All right, so our last video for section 3.3, we're going to prove a kind of a familiar fact, namely, if you have a function where the size is constant, then the function needs to be constant. Now, this is going to be a little bit more involved because sort of our functions are, if we think about them, they're functions of two real variables and they map to two real variables. But nevertheless, the result remains true provided f is analytic in some open connected subset of C. And then we'll argue that if your derivative is 0, then you have to be a constant. And that's also a familiar fact from calculus. So I'm just going to sketch the proof of both of these. So suppose that the modulus of f is constant. Now we're going to need to actually not use the modulus of f being constant. We're going to use the modulus of f squared being that same constant squared. And the reason is just that it's easier to differentiate the modulus of f squared versus the modulus of f. Okay, so if we were to write out the modulus of f squared, well, let me put it this way. If we write f is some real plus imaginary part, then the modulus of f squared is u squared plus v squared. And so u squared plus v squared is a constant, whatever that c squared was, the c for f. Now, we know some information about f, namely f is analytic. So f analytic is going to tell us that, well, the partial derivatives of u and v exist. And it actually gives us the Cauchy-Riemann equations that we'll use in a second. So in particular, we can partial differentiate this equation with respect to x, and we can partial differentiate it with respect to y. Great. Now, if we do this, let's see, we have to use a chain rule. So we get 2u ux, 2v vx, and the constant is a constant, so its partial derivative is 0. And similarly over here, we're going to get 2u uy plus 2v vy is 0. And so if you solve both of these, what you're going to get is u ux, u times the partial derivative with respect to x is negative v vx, and u uy is negative v vy. Great. So let's call these, well, this is what we have. And now we know that the CR equations hold because f is analytic. So this tells us then that ux is vy. I'm going to write it like this, negative uy is vx. So we're going to substitute out the v's in that. And if we take the first equation and we substitute out the vx, which is the only one we can substitute out with the Cauchy-Riemann equations, we're going to get vuy because the negatives cancel. And then the second equation, if we substitute out the vy for a ux, we're going to get negative v ux. There we go. Great. Cool. And so now we want to solve the system, so we need to find some commonality between the equations. And I see a common uy here. So maybe we can create the similar thing on the right-hand side and the left-hand side of the second equation. How can we do that? This is a v here. Well, we can multiply our first equation by u, and the no, this is a u here, sorry. God, I'm confusing myself. We can multiply the second equation by v. And when we do that, we're going to get u squared ux is uv uy. And we're going to get uv uy, oh, we have the commonality now, is negative v squared ux. Great. So now these just match on the nose. And so what we can do is we can then set the remaining sides equal to each other. So what do we get? We get u squared ux equals negative v squared ux, or equivalently u squared ux plus v squared ux is 0, or equivalently ux times u squared plus v squared is 0. Great, but u squared plus v squared, that's the modulus of f squared, that's a constant squared. Now one of two things happens here. Either the constant itself is 0, in which case f is f always has a modulus of 0, and the only output, the only value that has a modulus of 0 is 0, so f is the 0 function. So if c equals 0, f is identically 0. In particular, f is constant. Okay, so that's fine. Otherwise, ux is 0. And if ux is 0, you can do a similar argument, so ... to show that uy is 0, vy is 0, what am I missing? Vx is 0. In particular, the partial derivatives of the real and imaginary parts of f are 0. And if your partial derivatives are 0, then you actually have to be a constant function. So what this tells us then is that u and v are constants because their partial derivatives are both 0. They both vanish. U and v are constants. So f is a constant because it's u plus iv. All right, great. So so that is the first part. If your modulus is constant, u must be constant. This is a good fact to remember. For the second part, we computed actually f prime of z, and we showed it was two things. We showed it was ux plus I Vx, and we also showed it was uy, oh, no, not uy. We showed the Cauchy-Riemann equations hold. So we showed it was positive Vy rather, sorry. Vy minus, let me write that like this, plus I negative uy. And so for the second part, if the derivative is 0, then f is a constant. Well, the derivative we can compute in one of these two ways. And if there's 0, well, if the left-hand side is 0, that is 0 plus 0i, then ux and vx are 0, and vy and negative uy are 0. In particular, the partial derivatives are all 0 again, and so u and v are constant, so therefore f is constant. So I won't write that out, but it's the same argument.